Now we need to take another step. We're working in baby steps, and you're getting ready to walk, and you're going to make me so proud. All right, so in the previous video, we talked about this concept of a base peak, which is the tallest, and it's the most common fragment, as well as an M peak. And the M peak is basically the formula weight of the entire compound, right? That's what we said that we would go by. And we also took a look at a mass spectrum. Okay, so this is the one that we kind of saw in our last video. And I want to take a look at these two areas, the M peak at 72 and the base peak at 43. I'm going to bring up a calculator. The very first part of your job is to understand where these two fragments are coming from. All right? If you can't understand where the M peak fragment is coming from and where the base peak fragment is coming from, we have a problem. You can't go any further. So we have to be comfortable with this idea. So let's start with the M peak first. We said the M peak was the formula weight of the entire molecule because it did not get fragmented. Only thing that happened is that it lost an electron. So by definition, it did get fragmented. But as far as breaking up into pieces, all of the atoms stayed together. How do we get that 72? Why is that 72 there? Well, up here is the formula of the molecule that we injected. So that carbon weighs 12. Again, nominal masses. The hydrogen weighs 1 apiece, so that's 3. I have another carbon at 12. 2 hydrogens, so plus 2. I have another carbon at 12. Another 2 hydrogens, so we'll add those. Another carbon at 12. 2 more hydrogens, we add those. Another carbon at 12. And then 3 more hydrogens. Ding, ding, ding! 72. That's where the M peak is coming from, people. So this molecular ion peak is a CH3, a CH2, a CH2, a CH2, a CH3 that's lost an electron. So we have formed this radical cation that then goes through the system and it hits the detector out the other end. Everything stays together. Only thing that happened, it lost an electron, and that was it. All the carbons, all the hydrogens, all the oxygens, if they were present, stay behind. They stay together as a big group, and they get registered. But you know what? That's not the most common thing that happens when this compound goes into the mass spec. How do I know that? Because that is not the base peak. The base peak is something different. The base peak tells me this is the most common thing that comes through. Not the molecule in the entirety. Something else is happening. Something else is a little more common. So when this molecule goes into the electron beam, it gets fragmented. That's the most common thing that's going to happen to it. And I know that from the mass spectra. The mass spectra tells me. What's the most common fragment? Well, the most common fragment's 43. It weighs 43. How do we get 43? I play around with the molecule. So I'm going to bring up this calculator. I'm going to clear it out. How can we get the 43 here? Well, let's just start here on the end. I have 12 and 3, that's 15. 12 and 2 is 29. And then 12 and 2, oh, look, it's 43. People, it can't get any easier than this. People make mass spectra harder than what it should be. And this is as simple as it gets. That's all you got to do. You just got to add. Get your calculator. That's all you need. So what this mass spectra is saying, yes, I get a 72 peak. That 72 is present because the molecule as a whole goes through with a positive charge. That's how I get the 72 number. The 43 is the base peak. This is the most common peak that will come through. How do I get 43? Well, we just calculated it. We said we could do a CH3, a CH2, a CH2, and have that carry the positive charge. Because if that molecule fragments at this spot, this will get positive, this will get negative. Whoosh! That goes away. It gets sucked out of the machine. What I have left over is a 3-carbon chain with some hydrogen that carries a positive charge. That piece gets sent through the quadrupole, turns the bend, hits the collector plates, and then at the very end, we finally get a registered number of 43. Okay, but here's the deal. Notice what I did right there. I broke the molecule up in half, and I gave this side a positive charge, and I gave this side a negative charge. This is just one way for the molecule to fragment up. That's it. It's just one way. So I'm going to erase this. Other things can happen here. I can cleave the molecule in the same spot. But instead of giving the positive charge to the left, I'll give the positive charge to this side, and I'll put the negative over here. Well, that gets sucked out, never sees it. And the mass spec would see this other piece. All right, well, let's kind of add up that formula weight. 12 and 2, 12 and 3, 29. Oh, look, down here at the very bottom, I see a 29, and it's pretty tall. So we know that this 29 is coming from a CH2 and a CH3 piece that has the positive charge. We've just were able to pick out that fragment. Okay, well, let's play around with this molecule again. Now what I'm going to do is that I kept dividing it right here. All right, well, what if I took the dividing sign here? What if we broke the fragment up right there? Same deal. We get a 3-carbon chain. We've already identified that one. It's right up here at the top. And we get a 2-carbon chain. We've already identified that one. That's down here at the very bottom. So that's not going to change anything on us at all. Okay, so I'm getting rid of that. But what if we move that dividing line maybe here to the end? The same thing would happen if I did it here. No difference. The molecule's pretty much symmetrical, right? If I broke it here, I get a 1-carbon and a 4-carbon chain. If I broke it here, same deal. I get a 1-carbon and a 4-carbon chain. So we're just going to do this once and that's it. Well, there's 2 different options here. I could give this piece a positive and this piece a negative. All right, well, let's see what kind of fragments we would get from there. So I would get a 12 and a 2, a 12 and a 2, a 12 and a 2, a 12 and a 3, 57. Ding, ding, ding. Right there it is, 57. We come down. I now have identified that fragment. That is a CH2, a CH2, a CH2, a CH3 with a positive charge. Okay? Well, I'm going to go back and I'm going to erase these charges. No one says that this can't get a positive and that gets a negative. I'll just switch the pieces. Whoosh, that gets sucked out. What I'm left with is a carbon and a hydrogen. That's 12 and 3, which makes 15. I now have identified this one. And this 15 is coming from a CH3 group that carries with it a positive charge. Now, we've identified all the numbers except the 27. And I'm leaving this off for now because I just really want to keep it basic. I want to keep it simple. And when I say that, I mean I just want you to take a look at this compound. I want you to cleave it in 2 pieces, put the positive on one side, add it up. Then switch it, put the positive on the other side, and add that one up. And you will quickly start identifying where these numbers are coming from. So what this means is that if I take a look at the mass spectra, this molecule, 1, 2, 3, 4, 5, this is a pent, It's all single bonds from left to right, so this is a pentane. When I inject pentane into the mass spectrometer, what this tells me is that pentane will break up. It will. That's going to be the most common thing that happens. And the reason that I know that is because that's my base peak. My base peak will tell me what's happening most of the time. That's the tallest. It's the one that's the most abundant. And that 43 is coming from the molecule cleaving into two pieces. So when pentane goes into the electron beam, yes, it can stay together. Yes, it can be registered. I see that on the MS. But more so, it's going to break up. And it breaks up into two fragments. And the fragment that it likes the best is the positive charge on the biggest piece. My positive gets assigned to this 3-carbon chain. That gave me a 43, and that's how I got the 43 base peak. This gets sucked out of the machine. This 2-carbon chain, which ended up being 29, well, that never gets seen. But if the molecule breaks up, nothing says that the positive can't go here. It's just not as willing to go there, but it can. The negative can go on this side. It's not willing to go there, but it can. And I do see a 29 trigger. It's not as high, though, which means that that CH2CH3 fragment does not show up as much as the bigger fragment that carries the positive charge. The same thing's going to happen with my 57 and my 15. If I compare those and how they're made, we said that's what happens when we cleave it here. We have a 4-carbon piece and a 1-carbon piece. Well, my positive charge can go here with the 4, or in another scenario, it could go there with the 1. If I compare those two choices between each other, my 57 and my 15, the 57 is a little bit higher than the 15, and that's why. The positive charge typically likes the bigger fragments better. The same story happened with the 43-29 combo. The 43 was bigger. The positive charge tend to favor that bigger piece. Here, same story. 57's bigger, so the positive charge tends to go with the bigger fragment. But I can see both of them show up, and that's what I see on my chart. Again, we've not talked about the 27. We'll get to that a little bit later. But this is the mentality that you need to bring to the table. These are the pieces of information that you need to start taking away. How is it going to break up? Why does it break up the way that it does break up? Because there seems to be a trend here. The first trend is that it seems like the positive charges always go with the bigger fragments. And maybe that's something that I can take away. The other trend is that it looks like my combination of 43-29 is more preferred than the combination of 57 and 15. These two peaks are smaller, which means that if the molecule has a choice, it would prefer to do this. Why? We've got to talk about those reasonings too. And the issue here, and the reason that it does like to do it, is because this is an option for it to make the two biggest fragments. What you're going to find out with these molecules is that if they're going to break up, they're going to break up in a way that increases stability. And if they have just one little carbon that's floating around, this guy is super small, super tiny, and it's going to have a very hard time carrying a positive charge. In organic chemistry, maybe if you haven't got to that point yet, but you're going to start talking about carbocations. And carbocations are basically a positive charge that's assigned to a larger compound. And the more things that are attached to this carbon, the more stable the carbocation is. We're talking about size. The same thing's happening here. If the molecule has a choice, it's going to look at itself and it's going to say, okay, I'm going to break apart in the best way possible. And most of the time, it's going to break up into two pieces that are as large as they can be. It doesn't want to go this route of a 1 and 4 carbon. Yes, the 4 is bigger, but in exchange for that, it's getting just a 1 little carbon and that's it. It doesn't like that. It doesn't prefer that. It doesn't want that carbon on its own. So that is not as good of a choice as if it cleaved here, giving a 3 carbon and a 2 carbon fragment. They're bigger than that 1 carbon. They're more stable because of that, and they show up higher on the MS spectrum because of that. Okay, so you're just now on the ride of interpreting a MS. What we've done is just looked at numbers and kind of figured out where those peaks are coming from. And you'll have questions like this. You'll have questions that will say, identify these peaks, meaning what type of fragment is going to give rise to the peaks that we're showing on the spectrum itself. Here on this slide, you're basically seeing the same thing that we just did in a different format. So here is my pentane 1, 2, 3, 4, 5. This is my M to Z ratio of 72, right? Here is my fragment that gets the positive charge, and that fragment, away it goes. Notice that this electron dot is also there. Well, that electron dot's present because 1 electron got removed, meaning that we have a free electron that's swimming out here, and it left one of its partners behind. Most of the time they come in twos, but that's our cation. In the top case scenario, you see the cleavage site happening between carbon 3 and carbon 4. Or between carbon 2 and carbon 3. It doesn't matter. But we see a 2 carbon piece and a 3 carbon piece with the positive given to the 3. The same cleavage site, though, also gives us a 2 carbon piece and a 3 carbon piece where the positive could go with the 2 carbon fragment instead of the 3 carbon fragment. Next choice down below, I see it happen between carbon 4 and 5, a 4 carbon and a 1 carbon fragment. That's what I'm seeing here, 4 and 1, 4 and 1. I assign the positive charges to each one. That's how we get the 15. That's how we get the 57. That's how we get the 29. That's how we get the 43. If you can comfortably do this and kind of reason this information out, you're already a step ahead of the game. That's all that really matters in the beginning for mass spectroscopy. So that's where I'm going to stop this video. This is an introduction. In the next videos upcoming, we'll get into more nitty-gritty and talk about how these processes will happen.